Well, we don't have all the parts, but sans that, it should be working.
We got two of our things working. We just need to do the third one. We don't need to set it. I was drawing this. Oh, the final board. We're using the last one. We're not part of it. We're on the case then.
I'll keep that course online. Final project is just a little presentation.
Okay, so where do we begin? For those of you who weren't here before, we have a visitor today. Rachel Parker from the Ed School at Harvard, just doing some observation. So that's natural. Right, so we've had this bad habit for the past couple sessions where we kind of leave off in the middle of a proof, right? We were in the midst of proving that, I will remind you, if we have an analytic function in a disk, then the Taylor series of that function f uniformly converges on every closed subdisk, right? And I said that as an exercise, you all will prove to me that this proves that we converge pointwise everywhere in the disk, right? And in the closed subdisks, we converge uniformly. So right, we just skip to the uniform part, and then I'll ask you to show that shows pointwise convergence everywhere in the disk, right? Okay, good. So let's just remind ourselves where we were in the midst of this proof, right? So we expressed, let me draw this picture that we had on the board last time. Right, we have Z naught, and we have some open disk of radius r. Right, and we were interested in examining this closed subdisk of radius r prime, and we constructed this intermediary closed subdisk, which has radius the average of these two radii, right? R plus r prime divided by 2, and we had this auxiliary point z. We were looking at the Taylor expansion around this point z, right? Or actually evaluating at this point z. Okay, so here's where we got up to last Friday, right? We had this expression f of z is equal to 1 over 2 pi I times the integral. Oh, sorry, I should label this, right? This intermediary circle we call the boundary C, this positively oriented curve, right? So that we have some curve that we can apply the Cauchy integral formula for. Okay, so we take the integral around C of f of zeta divided by zeta minus z naught d zeta. Sum all the terms all the way up to z minus z naught to the n divided by 2 pi I times the integral around the same contour C f of zeta divided by zeta minus z naught to the n d zeta plus our error term, right? This is coming from, remember our general strategy so far was to take the Cauchy integral form expression for f of z and expand the integrand as a geometric series, right? From which we got some error term.
It's because we were taking like a finite portion of it, right?
Yeah, exactly. We were just taking up to the nth term, and then we're left over with an error term, which has the power n plus 1. Okay, so let's remind ourselves what this error term is. Again, the integral around the contour C. Now from zeta divided by zeta minus v naught to the n plus 1. Oh no, I'm sorry. I was looking at the previous term. Right? The error term comes in where we have this ratio all to the n plus 1. The zeta. And we call just this last term for brevity e sub n of z. The remainder, or error, see both of those terms in reference to a partial sum for a power series, or a Taylor series in this case. Okay, so, right, this is all recap. Our goal is to show that this error term approaches 0 uniformly for n in a certain radius. I'm sorry, for z in a certain radius, as n becomes arbitrarily large, right? We're looking to show uniform convergence. Okay, so I want to show e sub n of g goes to 0 uniformly. For z in the closed disk R prime, and goes to infinity. Right?
Can
Yeah.
you just remind me what uniform convergence versus piecewise convergence is?
Right. So pointwise convergence is the standard notion where remember we have these for every epsilon you have to be able to choose an integer n, capital N, such that for lowercase n large enough your term vanishes. Right? Here, when we make the definition of pointwise convergence, capital N is allowed to depend on z, the input of our function. Right? For uniform convergence, when we say something converges uniformly in some region, we're able to find a capital N that does not depend on z. Okay, so think of it this way. Pointwise convergence depends on the actual point that you're at in the region where you're describing convergence, whereas uniform convergence allows you to find a capital N that depends just on your epsilon, or, you know, that applies for all the z in the region that you're describing. Okay, so, yeah, and, you know, I gave you the definition of uniform convergence. I didn't review the definition of pointwise convergence, but just because I thought this is a somewhat familiar concept from Calc 2, maybe, right? Just in discussing sequences in series. But you'll review that on the final homework. Yeah, I'm saying something imprecise here, but it should be enough to get by, I hope, in class. Okay? Okay, so, right. Now, remind me what I said we would try to do to achieve this goal. We talked about this in brief on Friday. Right at the end, I was like, okay, so we get to this formula, which is fairly nice, right? Especially because we know we can express these the integral terms here as derivatives due to the Cauchy integral formula. But how will we show that this error term goes to 0 uniformly? Yeah.
So we have to bound the integral.
Yeah, exactly. We'll try to bound the modulus of this integral. Just like we've done many times in proofs, right? There's been no computational application of bounding integrals. I swear it does actually come up in the real world sometimes, but for our purposes, it's just basically a technique of proving things, right? If you can come up with a bound for an integral, you don't have to know what it is to show that it goes to 0. If you can arrange it so that n is in your bound, right? Okay, so let's pick this apart. Let's pick the integrand apart and see what we can say about the bounding of the modulus. Okay, so from the picture, what do we have? First of all, we have that the modulus of z minus z naught is less than or equal to r prime, right? Okay, and furthermore, the modulus of zeta minus z naught is equal to r plus r prime divided by 2. Right? That is to say, zeta is some point on our contour C. Right? That's what allows us to define these integrals. Right? We're taking zeta to be on the contour. Okay, so together, these imply that we can bound the modulus of this part of the error term as follows, right? 2r prime divided by r plus r prime, right? Which you'll notice here. Okay. So and also we have the following, and I'll ask you to tell me why. The modulus of zeta minus z, again, appearing in the, oh, sorry, this isn't the z naught, this is the z in the error term, right? Okay. So again, this term appearing inside the integrand. This has the following inequality related to it. Which, just by algebra, is r minus r prime divided by 2. Where does this inequality come from?
Fire.
Say again?
Is that a fire or is that just?
It's just the difference between the radius of the outer circle, or the, sorry, C, the contour, and the difference of like the radius of the inner circle.
Yeah, so this is essentially
the boundary of the circle radius r, and then zeta will be on our contour C.
right. That's
So that means it has to at least be that difference.
Mhm.
It's outside of the r plus r prime.
the triangle inequality, right? Yeah, that's exactly what you were saying, right? But just want to emphasize that things come back to the triangle inequality quite often, right? So okay, so basically now at this point we can bound the modulus of Tn of C. And we have all the components less than or equal to 1 over 2 pi, this being the constant up front of the integral. Right? Just, the I turns into modulus 1 times the maximum over zeta on C of the modulus of f of zeta divided by r minus r prime divided by 2 times 2r prime divided by r plus r prime to the n plus first power times the length of C. And this goes back to the one and only bounding theorem that we stated for integrals. Okay? So, this is to say, well, really there's not a lot to fill in here. Let's see, times 2 divided by r minus r prime times 2r prime divided by r plus r prime to the n plus 1. And what's the length of C?
I times r plus r prime.
Yeah, 2 pi, right?
Well, because it's r plus r
Yeah,
prime.
2, right? So two.
Yeah. I'm sorry, you're right. You canceled the 2's
Yeah.
for me. Sure. Good. Yeah, so let's just write it like that. Okay, great. So, first of all, we're trying to show uniform convergence. The important thing to note about this is that it's independent of Z. Right? That's good. Now what happens as n goes to infinity? I tend towards 0 because 2r prime is strictly less than r plus r prime. Right? Okay, so it's independent of Z. And since 2r prime is strictly less than r plus r prime, this tends to 0 as n goes to infinity. Okay. So there you have it.
Can we just get the fact that 2r prime is strictly less than r prime graphically?
Yeah. So, right, the graph embodies all the constructions that we made before. Yeah, of course, you could conceive of a different picture, but this picture is reflective of the analysis and the algebra that we stated in the lead up to this point of the proof.
And that's a fact because r is always bigger than r prime.
Yeah, exactly. Good. Okay, so here's what's going to happen. There's a handful of results about power series in general and Taylor series that will be very handy for us to have. But I really want to try to get to this whole thing of using Laurent series to do integration, right? Which it relies on the bedrock of these results on series, but the technical details of having proved them don't give us any advantage in evaluating integral systems. So I'm going to go a little fast here and harken back to what you hopefully remember from Calculus 2 about convergence of series. And if there's any questions, you can try to puzzle it out together. Just let me know. Okay? So. So before we actually start this down this road of this fast review of power series, let me ask, or maybe I should say point out, this theorem that we just proved about an analytic function a Taylor series for an analytic function converging to the function in some domain of analyticity. This shows what we've shown. A consequence of this is that the Taylor series will converge for the largest open disk where the function is analytic. Right? Okay, so keep that in mind. We'll call back to that sometime.
And then just a formal restatement that a holomorphic function is the same thing as an analytic function.
Yes, I'm glad you brought that up. So I wanted to remind us that this theorem is also the same as saying holomorphicity is the same as analyticity, right? That is, if a function is analytic in some domain, open connected set, then it must converge to its Taylor series there. Okay, so that extends for as big a domain of analyticity as you can have.
So entire functions have convergent Taylor series everywhere.
Yeah, that's right. Right. Okay, good. So, here's a practical theorem. Okay, so if F is analytic, at some point Z naught, the Taylor series of F prime at Z naught can be obtained by termwise differentiation. Of the Taylor series of F around Z naught, and more. And it converges in the same disk. Okay, this is again kind of a restatement of something that you may remember from Calculus 2, right? You can termwise differentiate and termwise integrate Taylor series to obtain Taylor expansions for the derivative or antiderivative respectively, right? But there's some consideration in Calculus 2 because we don't have the strength of analyticity necessarily, right? You have to concern yourself with what happens at the endpoints in the domain of convergence when you differentiate or integrate. Here, we're saying, by analyticity, you will have the same domain of analyticity when you differentiate. Okay? So I'll also ask you a kind of a nitpicking question about this on the next problem set. prepare yourselves for that. Okay. So, I always think this happens backwards, right? You start to talk about series representations of functions, and you define what a Taylor series is, right? And then you kind of pull the rug out from under you and tell you that there's a more general thing, a power series, right? Where the coefficients are not necessarily specified. Okay, so we'll do the same thing, I guess, since that seems to be the popular way to go about it. So this is another thing that has an analog in calculus 2 that I'm sure that you've seen. We'll state it again just because we're in a slightly different context here, right? That of analytic functions. Okay, so, right. For any power series, which of course just has the form, the sum from j equals 0 to infinity of a sub j times z minus z naught to the j. There is a real number r between 0 and infinity, inclusive, which depends on the coefficients. Of our power series. So that I have the following. One, series converges for the modulus of z minus z naught strictly less than r. The series uniformly converges on any closed subdisk the modulus of z minus z naught is less than or equal to r prime, strictly less than r. And thirdly, the series diverges for the modulus of z minus z naught, strictly greater than r. And as you may have guessed, r is called the radius of convergence. Okay, so maybe finally the word radius makes sense, right? Because we're actually talking about disks. When you do this in calculus 2, you're talking about intervals. It's like, why do we call this a radius? Well, because actually power series were studied first in a complex case. It's like, oh well, what is a radius of a ball on the line or a disk on the line? Just the endpoints of an interval. It's the length, half the length of an interval. Okay. So when I look back at when I took complex analysis, I think, boy, that was a relief when I was like, oh, the term radius actually makes sense here in a more traditional way. Right? Okay. So now we get to a stronger analogy to what happens in calculus 2. Notice in this statement, there's no specification on what happens on the circle of radius r. Right? Which, this is this whole business of like, determine the radius of convergence of a Taylor series for a function of a real variable. It's like, okay, well I can use, say, the ratio test or some other series test to determine the interior of the radius, and then I have to check the endpoints by like plugging things in and using a battery of other tests, right? This is analogous here. There's nothing to be said. In general, you have to check on a case-by-case basis whether or not the Taylor series converges on the circle that bounds the disk where convergence is guaranteed. Okay, so let's say that. Note, no general result. For convergence on the modulus of z minus z naught equal to r, which ironically we call the circle of convergence. It's completely silly to call it that, but we're kind of stuck. The circle of convergence. Okay. So, right. This is kind of a weird result, right? What is it about a power series that ensures that it converges on a disk shape? Why is it that any power series has a disk, possibly just a point, the completely shrunken disk, but still, some circularly shaped region must be the place where a power series converges. This is kind of odd. It seems like, a priori, you could just say, you should be able to construct a power series which converges on an arbitrarily shaped region, or maybe we should restrict ourselves to say simply connected or something. But in fact, it always has to be a disk. That's kind of the content of what this is saying. So I'm going to prove a lemma, and then give you a kind of informal justification of why this must be the case. So let's take a power series, sum from j equals 0 to infinity of a sub j times z to the j. And if this power series converges at a point having modulus r, little r, then converge at every point in this disk. Okay, so before we go on, let's just notice here, I'm looking at a slightly less general power series. It's centered at 0, right? That's why I can make a simpler statement just by looking at some complex number with modulus r, right? Because I'm centered at 0. Right. So this is the heart of the argument as to why this theorem holds. So let's see why this is true. Okay, so let's let Z1 satisfy the modulus of Z1 is equal to R. And we'll say that the power series with Z1 plugged in converges. Okay, so this tells us something. Now I'm gonna, sorry. Oh, that must have been outside. I thought you said something. Okay, so now I'm gonna lean on some results about the general series tests for convergence. Okay, so tell me if things get a little shaky here. Okay, so this implies the sequence of terms of the power series is bounded. What do I mean by that? There is a constant m so that if I take the modulus of one of my terms, the jth term, after plugging Z1 in, well, I know that this is just the modulus of the coefficient a sub j times r raised to the j, by our assumption that the modulus of Z1 is r, which is less than or equal to m for all j. Okay. So now let's look at what happens if the modulus of z is strictly less than r. Then for the modulus of z strictly less than r, we can write following: a sub j times z raised to the j is equal to, again, by the multiplicativity of the modulus function. You can pick this apart. Okay, now I'll do an algebraic trick the same as the modulus of a sub j times r sub j, I'm sorry, r to the j times the modulus of z divided by r raised to the j, right? I've factored this in a slightly unusual way. I took an r out and put an r in the denominator. Okay. So, which must be less than or equal to m times the modulus of z divided by r raised to the j power. Okay. So, what does this tell us? This tells us following, that for the modulus of z divided by r strictly less than 1, the terms of the sum from j equals 0 to infinity of a sub j times z to the j are dominated. And by dominated, I mean term by term bounded. That's just a sequence way of talking about boundedness, right? The terms of this series are dominated by the terms of a convergent geometric series. Right? These are the terms of a geometric series, right? And we know it converges since the common ratio is less than 1 by our hypothesis at the beginning of this board. Okay, so what convergence test am I building up to? What am I trying to say why this series must converge? Say that again?
Comparison test.
The comparison test, yeah, exactly. That is to say, if I can construct a series, I have some series in mind, right? Which happens to be the sum from j equals 0 to infinity of aj times z to the j. If I can construct a series that term by term bounds it, which converges, then I know my original series must converge as well. That's what the comparison test says. And that's precisely what we've done. So by the comparison test, the original series we were considering converges. Okay. So how do we find the R, capital R, from our theorem? That is to say, give me an informal argument as to how this lemma allows us to find a well-defined notion of what I said the radius of convergence is. So we know that the set of such little r in the lemma, where our power series converges for some point, is non-empty, right? Because it has to converge at its center, Z naught. Or in the lemma, that was 0, right? Because all the terms become 0. And we just have 0 equals 0. Okay? So the existence of a capital R, a radius of convergence, this maximum size circle, which bounds a disk where the power series must converge, follows from the least upper bound property of real numbers. You can find the least upper bound of this non-empty set of little r's. Okay? So this is akin to something we were talking about last week, or maybe 2 weeks ago. We descend into the axioms of the real numbers here to prove something about complex analysis. So yeah, again, this is kind of informal, right? Because we haven't made an axiomatic development of the real numbers, it's kind of a cheat for me to say that. But this is the fast way to prove it if you have the axioms of the real numbers on hand. Okay, so okay, now I guess I should mention, if any of these results seem kind of fishy to you that I say about convergence and various series tests, etc., section 4.5 of the textbook goes through everything in full detail. But again, I really don't think that's worth our time to go over something that I think you've seen in some capacity or another. So like when you look back at it, you probably will be able to get a pretty good feel of it on your own. Okay. All right. So now here's the real surprise. So for at the beginning of this past section where we started talking about power series, I said it was kind of odd how we introduce Taylor series, which are a specific type of power series, and then go back and say some things about general power series, right? Well, here's the big reveal. So every power series can be realized as the Taylor series of an analytic function. Okay? Which is a slightly different, there's a similar result in calculus of real functions. Again, less strong because of the strength of analyticity. Okay? So, here's a pair of theorems. I'll sketch the proof of one and say something slightly more precise for the other one. Okay? So, first of all, a power series sums to a function that is analytic at every point inside its circle of convergence. Okay, so say some really basic things. What do I want to say? Partial sums of a power series which is an infinite sum of z minus z naught to the j with some coefficients, right? If we truncate that at a finite stage, we get a polynomial. What's special about polynomials? They're analytic, right? First class of functions we examined that were analytic. And these polynomials, which are analytic, converge uniformly on any closed subdisk inside the radius of convergence. Okay? Just by what we showed before about power series, right? Or what I loosely justified to you, didn't really show everything. Okay, so, right. Here's the key thing that we skipped, which takes probably about half an hour of lecture to prove. But the thing is, analytic functions which uniformly converge in a simply connected domain converge to an analytic function. Okay? That's the thing that we're skipping the proof of here. This is why I say sketch. And that's a somewhat surprising result. But, for example, that certainly isn't true if you just assume pointwise convergence, right? Which, maybe that brings to bear what I said when we started talking about series, that since we're studying this strong condition of analyticity, we want a stronger version of convergence that preserves this property. This is one example of where we need that. Okay, so let me just say, this rather then use a lemma that a sequence of analytic functions that uniformly converge on a simply connected domain converge to an analytic function. Here's a hint of how to prove this. First, prove analogous result. For continuity,
No, I'm good. I have lunch. So I'm gonna lunch my EI lecture.
continuity, then use something that we called Morera's theorem. Anybody remember that off the top of their head? I wouldn't blame you if you didn't. This is the theorem that said if the contour around all closed curves in a physically connected domain is 0, then the function must be analytic that you were integrating. Okay, so some cryptic clues for how to prove this.
Could you say that one more time?
Yeah, sorry. Morera's theorem says that if the contour integral around every closed curve in a simply connected domain of a given function is 0, then it must be analytic. Right? We proved the converse of that several weeks ago, and then it takes a little bit of extra work to go the other direction, which is Morera's theorem. Okay. So, to finish this, then, you just note, any point z in the radius of convergence is contained in such a closed subdisk. Of course, I'll leave that open because I barely said anything there.
What do you mean by in the radius of convergence?
Okay, so I mean in the radius of convergence of this power
In
series.
that circle?
Yeah, contained within the open disk bounded by that circle. Remember, because in general we don't have anything to say about what happens on the circle. And then, yeah, so remember we also proved the stronger fact that this is the same as uniformly converging on any closed subdisk contained in that radius of convergence.
It's just a question like the in the radius of convergence. That word.
Yeah, maybe I should have said within the circle of convergence, right? Because that's kind of like the Jordan curve theorem version of it, right? On the inside or the outside. I mean on the inside of the circle of convergence. Okay. Let's take a break. It's really hot in here today, isn't it? Or is that just me?
I'm usually cold, so it's like really nice for me today.
It's comfortable. Okay. That must be the pressure.
Hi, Steve.
So yeah, let's meet in 5 minutes.
I never actually took Calc 2.
What did you say?
I never actually took Calc 2.
No, I didn't either.
So like, it's like I self-studied in 10th grade, like the series stuff, and I remember like none of it.
I did the same thing in 11th grade, and I also remember very little.
It's like I remember that like a of n plus 1 over a of n, and like is that ratio is less than 1 in convergence, and and there was like something to do with integrals, like the integral test, but I couldn't tell you how to do it.
I took the actual class in high school, but I had hip surgery halfway through. And so I was out of school for a week and a half, and then I was on painkillers for like another month. And so I don't remember any of that class at all.
Like the integrals, I can do integrals, but like, tell me to prove convergence, that's not what I'm doing. I thought I'd never have to recall it.
We've done a bunch of this in real analysis, so I'm kind of familiar with it now. I've been consistently surprised by the fact that I was allowed to take this class that I haven't done real analysis.
Yeah, right.
It feels kind of weird that it's just like the only prereq is Calc 3 to take this, but I guess it's been fun. Makes me more excited to take real analysis next semester. It's interesting. I enjoy it.
I can't take it until my senior year because like it's not open. Like the spots aren't open, and like I have to take like I'm on 12 next semester, and then I have like 3 physics courses I have to take next fall. And then I can't fit it in there. So I can only fit real analysis in. At the same time, I'm taking group theory, which is like the fall of my senior year. That's rough.
I wanted to take group theory and real analysis both next semester. If I do that, they have like the 3 same time slots, which is 8 o'clock, 9:25 or whatever, 9:15, and the 10:20 or the 10:30. I don't know if I want to do that. My only option is both of them right next to each other in the morning, 3 days a week,
It's a lot to undertake, but
I think I might just take one.
yeah, it wouldn't be all bad, I bet.
You gotta challenge yourself, you gotta push yourself.
No, I know it'd be like a lot of fun. Well, the learning the math would be a lot of fun, but like waking up Monday morning and going to like real analysis and then being like, oh, I still have group theory.
Yeah, I think that also has something to do with your taste. Like, you know, if you like analysis more, that might like get you juiced to go in the morning. I for one, I'm not much of a fan of analysis. I think complex analysis is my favorite flavor of analysis, but in general.
Where do your interests lie?
So I studied a lot of number theory as an undergrad, but then I did a lot more algebra, slanted towards category theory, and then eventually moving back to differential geometry in grad school. Yeah, so that's kind of where I am now. Categorical algebra and its tie-ins with logic and differential geometry. How's everybody's research going? Is that smoothly or?
But it'll take this break.
Okay, great. Yeah, I mean, you know, I didn't ask that out of concern. I was just curious.
I did very little this weekend because the Husky hunt was this weekend.
Oh, did you participate in that?
I did. So I spent all of Sunday sleeping.
Okay. Yeah, I guess that's kind of a marathon thing, right? You
Yeah, it's
kind of go until
Friday to Saturday, 7 p.m. So at like 7:30 I fell asleep and I didn't wake up until 3 p.m. the next day.
Okay. Well, that sounds fun.
It was good. It was a lot of fun. It's all about the like ciphers and sort of like cryptography kind of stuff. So it was a lot of fun to figure stuff out.
Yeah, that's cool. So, guess we should start again. All right.
Should we wait for Joe?
Yeah, we can wait for Joe. That's fine. I was just going by the time, but you know, I actually don't have as much as I thought. So maybe we'll actually get through everything I planned today. Which is not usually the case.
I think it's just been recently that we've had the long proofs right at the end.
Yeah. And we're poised to actually do that again, but instead, this time, I'm just going to draw a picture, and then we'll actually do the proof fresh when we come back.
Speaking of the lemma that we were talking about before, is there I'd love to try to prove it myself, but if I were perhaps unable to do so, is there something like in the textbook that it's shown or?
Yeah. It's, let's see, I might have that written down actually. I think, yeah, if you look at page 256 or 255, somewhere between 254 and 256. It's actually just a page, basically, it's broken into 3 separate results that lead up to this final statement that I said was the lemma. But yeah, of course, take a look when you are tired of trying to prove it, or after you prove it, just to see how you did it the same or differently. Okay, so let's start again. All right, so let's sharpen this theorem up a little bit, which is not, I don't say that in the precise sense of bounds. Let's make a more explicit statement is really what I mean. Let's say this power series, sum from j equals 0 to infinity, of a sub j times z minus z naught raised to the j converges to f of z in some circular neighborhood of z naught. Why do I take care to say it this way? Any guesses on this one? I know I have some non-zero radius. I'm sorry. I know I have some radius of convergence. Why do I insist circular? We also proved that it would always be a disk. But I say circular to disallow the case of a point. Okay, so I'm assuming here we have a non-zero radius of convergence for the purposes of this theorem. Okay, so let me write that. I.e. non-zero radius of convergence. Then, what can I say? The coefficient a sub j is just what you would expect. The jth derivative of f evaluated at z naught divided by j factorial. So the power series was a Taylor series all along. Okay, so this might shed some light on why things always seem backwards in the presentation of things. It's like Taylor series really are the fundamental thing that you want to consider in terms of doing calculus. But it takes some work to get to this point, right, where we realize that. Okay. Why am I guaranteed that these derivatives exist?
Because analytics functions have continuous partial or continuous or derivatives of all order.
Right, right, and we know that the function that a power series converges to must be analytic. Okay, we're just saying something specific about the coefficients now. Okay, good. Okay, let's prove this.
So this theorem just states that the concepts of a power series and Taylor series are like the same thing in complex
For analytic functions.
for analytic functions.
Where you can define a good notion of analytic function, right? So yeah. The development is a little bit different for real analytic things, but you can produce analogous results. Yeah, good. Okay. Here's the proof. Let's see. Positively oriented. Circle with center Z naught, surprisingly. Contained in the circle of convergence. Okay. As we were just discussing, f of z is analytic by our previous theorem. Okay. So let's apply the general Cauchy integral formula. Which says what? That the nth derivative of f evaluated at z naught is equal to, oh, sorry, forgot my constant out front. N factorial divided by 2 pi I times the integral around c of f of zeta divided by zeta minus z naught raised to the n plus 1 power d zeta. Okay, so where does that get us? Now, then plug in the series into the integrand for f of zeta. Right? Remember, we have this power series converging to f of zeta, so I gave you some glimpse of being able to do things term by term with power series, right? Or Taylor series specifically. So we'll just plug in that series development for f here and use the linearity of the contour integral to split it up. Okay? So what happens when we do that? We get the nth derivative of f evaluated at z naught. Okay. Yeah. Is equal to sum from j equals 0 to infinity of n factorial a sub j divided by 2 pi I times the integral around c of zeta minus z naught raised to the j divided by zeta minus z naught to the n plus 1 d zeta. Okay, so here's my claim. That I just get this. Why is this? I'll give you a hint. Way back when we first started talking about complex integration, I told you that there was a specific example that would come up again and again. We've seen it time and again when we proved both the Cauchy formula and the generalized Cauchy formula.
Because when you take the integral of 1 over z minus z naught for different powers of n, it equals 0 for all n not equal to -1, and then 2 pi I for n equals to -1.
Exactly.
So if you sum up all those, you just get 2 pi I.
All but one of these terms, the integral part of it will be 0. Yeah, good. Because we're just integrating a power of zeta minus z naught. Right? And only when that power is -1 do we get a non-zero term. And in that case, as Joe was saying, it's 2 pi I. Which cancels this. 2 pi I. It's 0 elsewhere. So we just get this. So let's record this. Okay? Since the integral along C, zeta minus z naught raised to the j divided by theta minus z naught to the n plus 1 d zeta is just equal to 2 pi I when, j is equal to n, and 0 otherwise.
This is kind of like an off-topic question, but is there like such a concept of like a negative derivative or like a fractional derivative or anything like that? Because would the Cauchy integral formula apply for those cases?
So there is such a concept as a fractional derivative. I think it was first defined in the early 90s. And in fact, there's not a lot of work that's been done on it. I think there's a lot of open questions about fractional derivatives. I certainly don't think it's been developed to the point of being able to be applied to, or have the methods of complex analysis applied to them. That's not to say that it can't happen. I just think it's a relatively young concept that hasn't gained much traction yet. So yeah, that would be interesting to know more about. I don't really know anything other than such a definition exists. I think I wasn't really ready to try to learn it when I first came across it, so it didn't stick with me very much. Yeah, if you decide to look into that, let me know, it'd be fine. Let us all know. Okay, anyway. So our coefficients are just what we'd expect, right? If I just divide by n factorial, both sides.
It just like the only reason why I ask is because that result is guaranteed if you take a positive derivative of n, like n equals 1, 2, 3, etc. Because you're summing from 0 to infinity for j. So j will equal n at one point. But if n isn't, like, if it's not a positive integer, then that result isn't guaranteed.
Right. And then of course, you have to talk about what factorial is. So that is a very well understood and researched question. That actually has to do with finding the analytic continuation of the factorial function, which is something called the gamma function, which is instrumental in formulating the Riemann hypothesis. So
And the gamma function still isn't defined for negative integers, is it?
that's right.
Yeah, so
Yeah. So
you can't take integrals using this form.
yeah. Yeah, so this is actually related to what we're going to hopefully get to today, just the basic definition of Laurent series. In fact, that's actually our next thing. Good segue. Let's now finally get to where we're going. I know this is somewhat, possibly somewhat unsatisfying, the amount of coverage that we've given here for results about power series, but again, I trust that you'll have no problem just looking over some resources and jogging your memory. Okay, so let's discuss Laurent series. Okay, so the general motivation, in a broad stroke, what we want to do is, up until this point, we've described the behavior of analytic functions, right? We'll now take the first step towards trying to see what we can say about computing integrals and developing series expansions for functions which may have singularities. And we remember what the definition of a singularity is? I mentioned it way back in chapter 2. So here's the general question. Can we come up with a series representation of a function near a singularity. So recall a singularity is a point of non-analyticity which is the limit of points where f is analytic. Okay, that is to say, it's I guess it kind of makes sense, the term singular, right? You're traveling along some curve, approaching a point, and you're analytic all the way up until you get to this point, and suddenly you fail to be differentiable. Okay. Okay. So it turns out the answer is yes. Yes, we can. When, for example, the singularity results from a vanishing denominator. Okay, who can tell me an example of a singularity that is not of this form, that does not result from a vanishing denominator?
Log z on the non-positive axis.
Yeah. So, right. Specifically, z equals 0, right? Yeah, you're right. The reason I bother making that distinction is because we already alluded to this, but the behavior of the bad behavior of the log function along the branch cut is slightly different than the behavior at 0, right? It's worse at 0, right? Which we'll come back to if we have time. But yeah, good. So, of course, I'll just record this. Not all singularities arise this way. Log z at z equals 0. But a lot of things that we've considered so far do have singularities that occur this way, right? Any rational function has singularities of this kind when you look at its poles, right? Poles are singularities that are of this form due to a vanishing denominator. Yeah?
Just a question about like at z equals 0. Wouldn't there be you have limits of all the analytic parts of log z for all points outside of the function disk, right? The non-real axis or the non-positive
The split
real
plane,
axis. Yeah. Would it not like change anything that the limit doesn't exist from the negative or the non-positive real axis? That's a singularity.
So So,
Then it isn't, it's only a limit for like almost every point, except for that one.
So there's a subtlety in classifying singularities, right? And it has to do with one of the subtleties, I should say. There are many subtleties. One of the subtleties is how many values a limit that goes toward a point, a singular point, can assume. Okay? That might not be clear what I mean by that, but suffice it to say, I really hope we get to this, but we don't have the machinery to discuss it really yet. Somehow the singularity at z equals 0 for log z is more essential. It can't be dealt with in any nice way. I'll try to make that more precise before the end of the term. Okay, so let's return to our discussion for this case where we have a vanishing denominator. Let me just tell you the theorem, and then I'll draw a picture, and I think we'll just call it a day. Okay. So, let's let F be analytic in the annulus. Given by the following. Little r is strictly less than the modulus of z minus z naught. It's strictly less than capital R. Where little r is allowed to be 0. In this case, what does our annulus become?
Punctured circle?
The punctured disk, exactly. Yeah, good. Okay. Then F can be expressed as the sum of the following series. Okay, so we have a power series going from j equals 0 to infinity of nj times z minus z naught to the j power plus the sum from j equals 1 to infinity of a sub negative j times z minus z naught to the negative j power. Okay. And what we'll say here is an exact analog of what we said for Taylor series of analytic functions. Only now we're working in an annulus, not a disk. With both series converging. In the annulus. And converging uniformly. On any closed subannulus. me take the trouble to specify exactly what I mean by this. I'll take some real number rho sub 1 less than or equal to the modulus of z minus z naught less than or equal to some real number rho 2 strictly less than capital R. Too much chalk today. Okay. Furthermore, there's coefficients given by the following. A sub j is equal to 1 over 2 pi I times the integral around C. Remember, this is suggesting that C is closed and we traverse it once in the counterclockwise direction. Okay, this integral of kind of our standard expression, f of zeta divided by zeta minus z naught to the j plus 1 power d zeta. Here, I'm letting j range through all integers, positive or negative. I haven't said exactly what C is yet. Where C is any positively oriented simple closed contour lying in the annulus with Z naught in its interior. And this is a theorem slash definition. This is called the Laurent series. F in this annulus okay, so a couple things of note here. What was the first one? What happens if F is analytic in this case? Notice in the statement of the theorem, there's no assumption that F is analytic at Z naught. But if it is, if F is analytic at Z naught, what does that tell me about my coefficients?
Does it all AJs for negative integer j or 0?
Yeah, exactly. If I'm analytic, then this reduces to the Taylor expansion. I'm analytic within, in the cutout part of the annulus. Essentially what I mean. Okay, so good. Let's say that. F analytic at V naught, you reduce to the Taylor series. Explain to me the meaning of this phrase. Or perhaps tell me why I say this specifically.
I mean, it could be outside CNOT and still in there.
Yeah, exactly, right? Here's an annulus. Here's a simple closed contour of positive orientation that does not have Z naught in its interior, but it lies entirely within the annulus. Okay? So I really want to consider things of this form. Okay? Right, so we have to be careful. We have this extra phrase is because we are choosing to use multiply connected domain. Right?
So it just means that the C has or can't be deformed into a point.
Yeah. Yeah. Yeah, maybe that's the more succinct way to say this, but 6 1/2 dozen of the other. Okay, right. So we've got 3 minutes left. This picture is kind of complicated. Let me just say a couple things. I'm not going to write anything down. We'll essentially go about this the same way that we proved the convergence of the Taylor series to an analytic function. Right? We'll again omit the statement that we converge in the annulus in favor of just proving the stronger fact that we converge uniformly on every closed subannulus. Okay? And then the same argument that you're going to make for the next homework will apply here as well, to show that that gives you convergence on the whole annulus. Okay, so in order to do that, what we'll do is do a very clever piece of contour integration, where we look at an annulus and we're going to break it up into 2 pieces, right? A piece that goes like this, right? This little chunk out of the donut, and then a piece that goes like this to here, and it goes in, then it goes counterclockwise, or I'm sorry, clockwise on the interior circle until we get to here, and then it comes out and goes back around. Okay, so we're going to compare, oops, sorry, went past the line there. We're going to compare the contour integral around the boundary of this chunk to the contour integral around the boundary of this chunk. And that's our first step in producing this development, this series, which is a sum of 2 different infinite series. Okay. So, have a good Thanksgiving break. Feel free to email me about any research questions about the final project or whatever. I'll see you next Tuesday.
Nice to meet you guys. Have a good